Okay. So, I am going to be taking this skipgram model as an example, and I am going to be showing some small pieces of code. It is not complete code, and I am going to be providing only the pieces of code for you as well. Your job is to really take this code, integrate and make the application run. So, I will not be giving all the details, every line of code and so on. I will be giving only pieces of code for you this time. Okay. Not like last time where I gave you the full code. Okay. So, for any network to work, we have to do some kind of an initialization. We need to first set up our corpus. I am taking a very small corpus of about 100 documents. It is very small. It is not good enough to really identify all the word vectors in the right context. Okay. This is just to show how it works. Okay. So, I will be initializing some parameters. Initially I set up the corpus, so that I can read all the documents, and then I initialize the model parameters. In this case, I am taking the context window. You remember we will be having the context window, where we will be looking at okay. In the skipgram model, I will be inputting this, and these are the context word the application is supposed to predict. Okay. So, I have the number of epochs, and then the context window size, and the these are the initialization that you can provide when you start the program. Okay. And then you initialize the weights. As I mentioned earlier, the initially to start with, you have to have some weights associated with that. So, I am just using a random number using a uniform distribution between the values of minus 0.9 to 0.9. I initialize both embedding weights as well as context weights here, okay, using this. Okay. So, this is the second step that you have to do. So, you initialize all the parameters and then initialize your weights, and then we start the forward process. So, what is the forward process? We know that we need to identify the H. So, we have our X here, okay, and then we have our embedding matrix, and then we need to find the hidden values. Okay. So, in the forward pass, what we do is we just you take the transpose of the weight matrix and then take a dot product to get H. Okay. And then what is the U? U is your the final value that is calculated using the hidden values and the context matrix, correct. This is one step before softmax, all right. So, in one go I compute the forward pass. Okay. So, you know what is the input that you are providing, and then once it is done, H is calculated, and now U can be calculated using H as well. Initially these weights, as I mentioned earlier, are random weights. So, now you compute y hat. Y hat is your softmax values. Okay. So, using softmax you find the y hat. So, we have H here, and then you have the context matrix. Now, we will give you U, and then this results in y hat. Okay, and then I return all the three values in one go. Okay. So, we have computed H, U and y hat in the forward pass. How easy it is, right. So, then now you have to do the back propagation. So, U is computed, softmax is computed. So, find the error. Now, we have the equations for your convenience. I have provided these equations. So, we need to update the weights in the context matrix using this form, right. So, for that you need to find the difference, right. So, what is the difference that you want to compute, and then later use the difference to find the new values. So, this is what we are doing here. So, we do it for the context matrix, okay, and then do it for the embedding matrix, and then update the context weights. So, the new weights are updated using the old context weights, and then use a learning parameter, and then use the delta context weights which we computed earlier here, and get the new context weights. So, once the context weights are obtained, we now go back to the embedding weights and then update it as well. Again, using the formula, we are going to be updating the embedding weights. So, we have the old embedding weights here, and then use the same eta parameter, and then use the delta embedding weight that we computed earlier to find the new embedding weights here. So, this is your new value, right. So, in about 5 lines we have done the back propagation part, right. And then how do you keep doing this, right. So, we need to have the error parameter that needs to be minimized as given here, and that will be incorporated as part of the training process. And then every time when those weights are computed, when the errors are computed, we want to find out whether the value of E minimizes. Okay. So, when it keeps going down and down, so usually you get something of this type. Okay. This is your error, and this is the number of APOs. Okay. So, we need to keep looking at this. Initially it will be random. To keep a tab on this, right, when you start doing the training part, and then see how it goes. Sometimes if you have not done your implementations right, okay, it will be very erratic in this fashion, or if the learning parameter is not appropriately chosen, it will also not be in this fashion. So, sometimes it will come down and then go up and then try to come down like this. Okay. So, make sure that you get something ideally in this fashion. Okay. So, this is something that you want to get at the end. Okay. So, here what we do is we just do the forward pass as I had shown earlier, and then we keep computing the EI part, okay, for every word, and then compute the back propagation. Okay. So, this particular instruction, what it does is it actually computes the error for every context word. You remember in the first slide when I was talking about we have the target, right, and then this is the predicted value, and then we found the error, right, for a bigram where we have only one target word and the context word. So, now we have more than one context word. So, that means we will have more error values, correct. So, let us say this is 1, this is for the first context word, target 2, predicted value 2, so error 2. So, when you compute the error, you do it for all elements or all the words. Okay. So, the size would be same as T1, T2 and so on. Okay. So, in the same fashion for the second word you compute, for example, initially this is our target and this is our prediction. Even though we are only finding the difference for this, but we also find the difference for all the elements, right, and then they go here. So, in the same fashion for this word we calculate error 2 and so on. So, in this fashion if you have about 5 or 4 we need to compute the sum of all this. So, in this case what we do is we and then finally we get one E from all this, right. So, the E size also is same as the size of our vocabulary. So, all differences are summed at the end, and this is what is happening in this step. Okay. So, once it is done, use the back propagation to update all the weights. So, you remember in the back propagation we are updating both the embedding weights as well as the context weights. I am sorry, in the order of context weights and embedding weights, and then compute the error for that particular epoch. Okay. So, using this formula. So, we have given here, and this is the error that you have to keep looking at. If this error goes down in this fashion smoothly, you are doing good. Okay. So, if you have something in this erratic fashion, something is wrong. So, do not start with 1000 epochs immediately, do not start with 1,000,000 vocabulary immediately, start small, take about 10 words as vocabulary, 5 epochs, and then start looking at this. Okay. So, make sure that your program is right, make sure that the error is slowly coming down, then you can really take a bigger corpus, bigger vocabulary, and then increase the number of epochs and so on. So, while doing that, keep playing with the learning parameter to see what is the right learning parameter for you as well. Okay. So, you got it. So, when you look at it through the program, sometimes it looks so simple. So, that is why I thought I will also take this route rather than just explaining the equations, rather than just giving them in the matrix form. I thought I will also give the program so that you can follow that. Okay. So, after completing the exercise, okay, we now have embedding vector. Okay. So, each row represents a word vector for you. Supposing you have about 300 words. Okay, this is word 1 to 300. So, each vector will have, let us say, 300 to 500 elements depending on what you have chosen as the hidden value size. Okay. So, what I have done in this case is I have trained that very small corpus which contains problem statement related to kinematics, and then I trained the vector, and each problem is about 1 or 2 lines consisting of about 20 to 30 words max. Okay. I have taken one word and then I am just trying to find out what are the similar words in this. So, the kinematics problem, there are problems where you are dropping a stone into a well, and then the sound was heard after few seconds. How deep is the well? Okay. So, like that there are several problems of that type. So, I just wanted to find out how this word deep is related to the words that are surrounding it, or I just wanted to find out the words that really define deep in this given context. Okay. So, once the program reaches an equilibrium state, we do not need the context weight part, we do not need that softmax, we do not need any of those. What we require is the embedding matrix. Okay. So, now I take one word deep as a word, and then I take the vector out of that and then run it through all the vectors, word vectors here to find the similarities. So, I use a cosine similarity, I am sure you remember that, and then find out the values, and then listed them top 10 or 15 of them to find out how close those words are in the given embedded matrix. Okay. So, you will see that heard, depth, will, sound, peso, there is a coin used, and then hit, after how many seconds you heard water. So, all of those words are related to deep in this case. Okay. So, it varies from 0.77 or rather 0.8 to 0.4. Okay. So, if you want still closer ones, you do not want beyond 5 or 4, this is how you got it. So, in this case what I have done is I ran through the word vectors through the entire set of words or the vectors that was found through the model, and then found the similarity and then listed them in the descending order. Okay. So, you get this right. This is the most crucial part in the natural language processing, where you need to really create word vectors for the given context and the corpus. Okay. There could be a general purpose word vectors that you can also create by looking at the content available in the internet, by taking close to 2 billion or 3 billion words, say for example, extract close to 3 billion words from Wikipedia and then start training using the skip-gram model and so on. So, as I mentioned earlier, the implementation that I have shown uses a skip-gram model. All right. So far what we have seen is how this model works, right. We also have mentioned earlier that the size of the network really matters, correct. If you start looking at the larger corpus where you have more than 1 million word as your vocabulary, I am going to be having 1 million one-hot vectors, right, and then every one-hot vector will have 1 million elements, and then correspondingly you have a 1 million into, let us say if you restrict the hidden layer size to 300, 1 million into 300, and then if you go to the context side, again you have the matrix operation that you have to perform for the matrix of size 300 into 1 million, and then we have a U that is 1 million element, we have a softmax that is 1 million elements, and then the different that will be 1 million elements and so on, right. So, look at the size as the number of words in the vocabulary grows.